Hello, I'm Lu Yu from Zhejiang University, China. This is a talk on learning-based image and video coding for CVPR 2020, Workshop and Challenge on Learned Image Compression. There are two major system architectures for learning-based image and video coding. One is embedding neural network modules into traditional hybrid coding framework. The other is end-to-end coding. The organizer of this workshop invited me to give this talk, majorly focus on the first kind of architecture. I guess maybe the participant of CVPR may familiar with the end-to-end coding architecture. So I will pay more time to introduce the research results on the network-based hybrid coding. Other than that, at the end of my talk, I will also introduce some latest information about coding, not only for human vision, but also for machine intelligence. I believe people working on coding understand that we compress image and video following the theory of source coding. There are two threads of compression: the characteristics of source signal and characteristics of human vision. The existing of spatial temporal correlation leads us to prediction and transform. The existing of statistical correlation leads us to entry coding. Because of the limited sensitivity of vision, we can conduct a quantization. I will start from in-loop filter. It is an important module in hybrid coding and helps to improve reconstructed quality of video. Neural network can be good at acting as filtering. So learning-based in-loop filter caught the most research interest in all modules of hybrid coding. Here, a deep CNN is proposed for in-loop filter. It may replace the deblocking filter and sample adaptive offset filter for intra-frame, and added between deblocking filter and SAO as a switchable module for B and P frames. Significant coding gains can be obtained by using such a deep CNN, but the network module is sensitive to quantization, so different modules have to be trained for different QPs. But people try to avoid use deep neural network for complexity reasons. So here a 4-layer CNN is proposed for in-loop filter in 2017. By using reconstructed pixels from previous frame and insert the new module after deblocking and SAO, some coding gains can be reached, even though it is not so good as that from deep neural network. And also different models have to be trained for different QPs. In this work of 2018, normalized QP map is introduced as additional input of a 8-layered CNN. Now the same model can be used for different QPs. The module replaces the bilateral filter, deblocking filter, and SAO in-loop filter. Residual values can also help when a less layered CNN is used as in-loop filter. When block partitioning is introduced into a deep neural network, more than 7% of BD rate saving can be reached by learning-based in-loop filter. As a short summary of neural-based in-loop filter, they are kind of content adaptive filtering, which can be inserted into different positions of the in-loop filter chain, from deblocking, SAO to ALF, or replace some parts of the existing chain. Additional information other than the decoded frame can help to perform, including temporal neighboring pixels, maps of QPs, block partitioning, prediction residues, and deep neural network can obtain more gain than less layered ones. A second module well studied in the hybrid coding framework is the intro prediction. Convolutional neural networks are used to refine intro prediction blocks. This module may replace all existing intro mode and a small coding gain shown. The second work proposes to use a fully connected neural network to generate a predicting block directly from neighboring reference pixels. The neural network generated prediction block is used as an additional mode and can be selected at the CU level. And it is studied to use same or different models for angular and non-angular modes. Here, recurrent neural networks are proposed to generate prediction block for intro prediction. After the feature extraction by CNN, RNN units are used to generate prediction of feature vectors. And in the training of neural network, energy of residues in both spatial domain and transport domain are considered in the loss function. These neural networks brings coding gains and in the meantime introduce significant complexity. So a single layer network is studied for generation of intro prediction. First, a 2-layer neural network is trained, in which the first layer extracts a feature from the reference pixels, while the second layer makes the prediction. Then the neural network is simplified by pruning and removing nonlinear activation function. Additional to that, a 2-layer neural network is used to predict the conditional probability of each intro mode, and the intro modes are sorted by probabilities, and a most probable mode list is generated accordingly. 3.8% of bit rate saving is shown by such a simple network. A short summary for intro prediction. Prediction could be for pixel values, including refinement of traditional prediction or extrapolation from reference pixels directly. Prediction can be conducted in spatial domain or transform domain. Learning-based intra-prediction could be a supplementary or replacement of traditional modes. Either CNN, RNN, or fully connection networks or their combinations can be used. And the loss function can measure mismatch in either spatial or transform domain. Prediction could also for the probability of intramodes. This also helps saving coding bits. The third well-studied module in hybrid coding is interprediction. First of all, subpel interpolation is studied. Here, a 4-layer CNN is used for super resolution. It directly replaces the traditional DCT-based interpolation filter. Again, different models are trained for different QPs. Then in this design, 3 4-layer FRCNN are proposed for different half-pair positions. The CNN-based interpolations are used as an optional additional interpolation mode other than DCT-based ones. While in this design, one model can generate pixels of different subpel positions by extraction a shared feature map and only one layer of network for variations of different subpel positions. Considering of complexity, a less layered neural network is proposed. And to balance the performance, special training schemes is introduces. Additional to interpolation filter, neural network-based filter are proposed to refine interprediction blocks. So here, L-shaped neighboring pixels are introduced to the neural network to refine the unit prediction block. A 4-layer VRCNN is used here. It's a switchable supplementary to the existing interprediction. Additional to that, L-shaped neighboring of current block and also reference blocks are introduced here. Now, fully connected network and CNN are used. Besides the refinement of existing prediction from traditional ways, predicting blocks can generate directly from reference blocks by neural networks. By introducing temporal distance, by prediction blocks can be generated from the reference blocks and generalized for temporal interpolation and extrapolation. Here, 4.8% of bit rate saving is reported for learning-based interprediction. A short summary for interprediction module. Neural network can be used for prediction of pixels of blocks as well as prediction of motion and optical flow. For fractional pixel interpolation, it's quite similar as a super resolution issue. For refinement or directly generation of prediction, Spatial and temporal references can work together, and the unidirectional and bidirectional multiple hypothesis prediction can be generalized by introduced temporal distances of frames. And the prediction can be generated either without motion vector or with motion vectors. And the network-based prediction can be used as a supplementary intermodes or replacing two traditional ones. Transform is another module utilizing spatial correlation in the hybrid coding framework. Here, CNN to analyze features in the original blocks together with a fully connected layer to fulfill the transform is proposed to be used in the image coding. And DCT transform matrix are used as initialization for the fully connected layer. And the CNN and the fully connected layer are jointly trained. Quite good coding performance demonstrated compared to DCT and the coding method of JPEG. An interesting question is whether it is still good for prediction residues. I expected to further study on this topic. Quantization is a module Lakoff studied in learning-based coding. One possible reason is it's related with perceptual characteristics, and we are lack of dataset on it. But there are still a lot of studies on the optimization of quantization parameter selection. Since these are not new coding tools, I will skip those things. Entropy coding is an interesting module that learning can help. So here's an example that probability of intra-prediction mode are estimated. Reconstructed pixels as well as prediction modes of neighboring blocks are input into the network, and a vector of probabilities of all 35 intramodes are predicted by the network. Significant coding gains is demonstrated. Another example is a probability estimation for transform kernel index. Here, transform coefficients are used as threads to estimate the probability of transform selection. A convolutional neural network together with a sampling and full connected layers are proposed. Then the estimated probability is used to reorder the transform kernel indexes. Some coding gains are shown even with such an index. A larger proportion of the bit stream is related with residual coefficients. So here the probability estimation for the intra-prediction residuals. Probability distribution of syntaxes such as last non-zero value position, DC value, and the first to the sixth AC values are estimated by a neural network. A short summary on learning-based entropy coding. All studies are focused on probability estimations for different syntaxes using correlation information such as reconstructed pixels, decoded neighboring modes. One thing I would like to notice is that the labels we used in the training are the happening of the value, which means the possibility instead of the probability should be estimated. Here, the possibility describes the likelihood of a value happening in one symbol, while probability describes the frequency of the value happening in an infinite stream of symbols. This concept was proposed in one of my papers in 2018. So in fact, we are estimating the possibility, but not the probability. The inaccurate of the estimation may cause the bits of coding. This figure shows the performance of learning-based coding tools, in-loop filter, inter and intra prediction, as well as entropy coding can all benefit from learning. These performances are all compared with the anchor of advanced video coding standards such as HEVC, but we don't have enough examples for transform and quantization. So here the transform result is only compared with JPEG. After so many researchers on learning-based coding modules, can we integrate them into one hybrid systems or end-to-end system? In fact, there are some researchers to ensemble different modules into end-to-end coding systems. So here networks for residual coding, motion vector coding, and optical flow estimation, as well as bitrate estimations, are ensembled into one system. And here, 3 end-to-end networks for intracoding, intercoding, and residual coding are integrated into one end-to-end video coding system. Coding results outperform HEVC is already demonstrated. A conclusion to the learning-based image video coding, let's say all roads lead to Roma. Hybrid coding framework embedded with neural network-based modules can bring significant coding gains. End-to-end framework can be explained by traditional source coding theory, because it's also combined of prediction, transform, quantization, and entropy coding modules. The boundaries between these two architectures are blurry. For both architecture, the coding performance may come from nonlinear reorganization of information, vector quantization, possibility estimation, by multiple complicated correlated contexts, which are not well covered by traditional coding tools. Before I end up my talk, let me provide some informations on the learning-based coding. So the first is there will be a special section on learning-based image and video coding in IEEE transaction on CSVT. There will be 12 papers in this special section, one on end-to-end compression, the others on intra-prediction, inter-prediction, in-loop filtering, arithmetic coding, and also encoder optimization. And for your information, recently an ad hoc group on deep neural network-based video coding was established in MPEG. We will study the performance improvement potential of deep neural network-based video coding technologies and the coding and decoding complexities will be studied in the group. If you are interested about this activity, you may subscribe to the mailing list. Additional to that, people are considering of image video coding not only for human vision, but also for machine understanding. So the potential usages could be like smart industry, intelligent transportation, smart retailers, smart cities, smart sensor networks, immersive video and for entertainment, smart media editing and creations. It could be machine-oriented or hybrid of machine and human representation. In the video coding for machine, you may consider to use existing video encoder-decoder to serve for the machine understanding. You may also consider to develop some new techniques to compress features extracted from video. And in order to serve also for human vision, some additional bitstreams may be provided with new video codec. In MPEG, another ad hoc group on video coding for machine established in last year. We are planning to call for evidence in this July. If you are interested about this, you may also subscribe to the mailing list of the ad hoc group. That's all for my talk. Thank you very much. If you have any question, please contact me with an email. Thank you.